Okay, so we introduced this concept of the orbital as a region of three-dimensional space that describes where we expect to find electrons relative to an atom. That is really relative to the nucleus of an atom. And so these orbitals are the solutions to the Schrodinger equation that we can calculate for relatively simple systems. And we defined a number of possible uh, solutions for different atoms. And these come into four different general types of orbitals. That is, there are s orbitals, there are p orbitals, there are d orbitals, and there are f orbitals. And you hopefully recall that these designations, S, P, D, and F, correlate to the different subshells in our modified Bohr model of the atom. And so a lot of the same language that we use in the Bohr model and a lot of the same ideas in the Bohr model are maintained in this quantum mechanical model. But instead of talking about electrons existing in different discrete shells, we say that these electrons exist within different types of orbitals. Okay? And the first of these are called the s orbitals. And these s orbitals are perhaps the simplest, and they are all spherical in shape. That is, they describe a spherical region of space centered at the nucleus within which we expect to find the electron at a given energy level. So at the 1s energy level, we have our 1s orbital, which is simply a spherical region of space. Now, as n increases, that our principal energy level or our principal quantum number, basically these s orbitals just get larger. So we can have our 1s orbital where we expect to find that electron somewhere in here and not somewhere out here. We could have our 2s orbital, which is much larger than our 1s orbital, and the 3s orbital is larger still. Now, as we increase in size and increase the number of n, we also introduce regions represented by this white area that we call nodes. And these nodes, again, are related to the wave-like properties of these of electrons and in fact of their distribution. These are regions where there is no probability or zero probability of finding that electron. And we're not going to be too concerned with the impact of these nodes at this point in time. What we really want to understand that as the value of n increases, this energy of our electrons within these orbitals increase, and also the size increases. So I think this cartoon right here really demonstrates the salient features of the s orbitals. Going from 1s to 2s to 3s, the size of these orbitals gets significantly larger. And so for a 3s orbital, there's still very significant probability of finding that electron way out here, whereas for a 2s or a 1s orbital, we would never expect to find that electron. That is, there is very little probability that that electron exists for a 1s orbital way out here, this type of distance from our nucleus. So those are our 1s, 2s, and 3s orbitals. Now, the next type of orbitals that are important to us are the p orbitals. Okay, so these p orbitals are very different in shape from our s orbitals. And in fact, there are three different types of p orbitals, all of approximately the same energy. Okay, each of these orbitals is what we call bilobal. Some people call this dumbbell shape. That is, they describe two regions above and below a plane that have a high electron probability density. Okay? In between these two lobes, there is a node, which once again represents a region where there's no high electron probability density. That is to say, for a p orbital, we wouldn't expect to find these electrons too close to the nucleus. So that electron might be somewhere up here, it might be somewhere up here. Okay, so we have three different types of these p orbitals. So for s orbitals, they're always spherical, right? They're always the same shape. But for p orbitals, we can have those two lobes oriented along the z-axis of an xyz coordinate system, a Cartesian coordinate system, or we can have a p orbital oriented along the x-axis, like this one, or we can have a p orbital oriented along the y-axis. So we can call these p sub z px, and py. And really the designations are not terribly important for us at this time, but what we want to understand that each of these orbitals are regions of space where we can expect to find electrons that occupy these orbitals, okay, that occupy these particular energy levels. One is oriented in one direction, and then another direction, and the third one is oriented along that third axis of our XYZ coordinate system. Okay. Now, one thing we want to avoid thinking about is that we sort of look at this and think, oh, we want to avoid thinking that this electron is zipping around in a figure-8 racetrack here, going back and forth like this, when in fact, again, we don't imagine that these electrons are following a given trajectory. That is, they're not orbiting around the, uh, the nucleus in a particular path, but rather these orbitals simply say that that electron may be somewhere up here and it may be up here. And we don't want to get stuck into a question like, well, is it here or is it here? Because that's not, it turns out, a very useful question, because the answer to that is simply yes. It is here or here, and we don't really concern ourselves with whether it's up here or down here. Okay? So these are our p orbitals, and again, these p and s orbitals are our most important orbitals that we are going to consider. Now, there are also d and f orbitals, and we won't really spend any time discussing these further, other than to say that these are additional orbitals that describe regions of space within which we can find the electrons. Okay, so in the case of the d orbitals, there are 5 of them, and they have the shapes shown here. Sometimes they're called cloverleaf, arranged in different orientations, like these 4. Or then there's this really weird one, which looks like a p orbital with a donut around it. Okay, we're not going to be too concerned with the shapes of these d orbitals, as they're a bit beyond the scope of this course. But suffice it to say that there are these different d and f orbitals that have different shapes, and again, these shapes simply represent a region of space where we expect to find electrons in a d orbital or an f orbital at the appropriate energy level. In our next quick video, we're going to sort of understand the relationship of these 5 different orbitals and the relative energy of electrons in a similar manner that we started to talk about in the context of the Bohr model. And it is really important that when we think about these orbitals, this idea of electron probability density is a little bit abstract. It's something that's sometimes hard to visualize, and I think that's best seen in these p orbitals, right? We don't know if the electron's here or here, and we kind of have to think that it's all over the place at the same time, which, you know, it can't be everywhere at once, but it's because it's describing the atom, and where these electrons are in terms of a statistical model, in terms of probabilities. It's a little less satisfying than our Bohr model, which, while the Bohr model was incorrect for reasons we've discussed, it's a little unsatisfying. And so what we're going to do is we're going to have an understanding of these orbitals and really sort of transpose them onto that simpler Bohr model, which is a little easier for us to visualize. So in the next quick video, we're going to talk about how electrons are arranged within these different orbitals, and how to predict the arrangement of electrons using something we call electron configuration.